Life cycle assessment is a technique to assess environmental impacts associated with all the stages of a product's life from cradle to grave, that is, from raw material extraction through materials processing, manufacture, distribution, use, repair and maintenance, and disposal or recycling. LCAs can help avoid a narrow outlook on environmental concerns by compiling an inventory of relevant energy and material inputs and environmental releases, evaluating the potential impacts associated with identified inputs and releases, interpreting the results to help make a more informed decision. Goals and purpose. The goal of LCA is to compare the full range of environmental effects assignable to products and services by quantifying all inputs and outputs of material flows and assessing how these material flows impact the environment. This information is used to improve processes, support policy and provide a sound basis for informed decisions. The term life cycle refers to the notion that a fair, holistic assessment requires the assessment of raw material production, manufacture, distribution, use and disposal including all intervening transportation steps necessary or caused by the product's existence. There are two main types of LCA. Attributional LCAs seek to establish the burdens associated with the production and use of a product, or with a specific service or process, at a point in time. Consequential LCAs seek to identify the environmental consequences of a decision or a proposed change in a system under study, which means that market and economic implications of a decision may have to be taken into account. Social LCA is under development as a different approach to life cycle thinking intended to assess social implications or potential impacts. Social LCA should be considered as an approach that is complementary to environmental LCA. The procedures of life cycle assessment are part of the ISO 14000 Environmental Management Standards, in ISO 14040 2006 and 14044 2006. GHG product life cycle assessments can also comply with standards such as PAS 2050 and the GHG Protocol Life Cycle Accounting and Reporting Standard. Four main phases. According to the ISO 14040 and 14044 standards, a life cycle assessment is carried out in four distinct phases as illustrated in the figure shown to the right. The phases are often interdependent in that the results of one phase will inform how other phases are completed. Goal and scope. An LCA starts with an explicit statement of the goal and scope of the study, which sets out the context of the study and explains how and to whom the results are to be communicated. This is a key step and the ISO standards require that the goal and scope of an LCA be clearly defined and consistent with the intended application. The goal and scope document therefore includes technical details that guide subsequent work, the functional unit, which defines what precisely is being studied and quantifies the service delivered by the product system, providing a reference to which the inputs and outputs can be related. Further, the functional unit is an important basis that enables alternative goods, or services, to be compared and analyzed. The system boundaries. Any assumptions and limitations. The allocation methods used to partition the environmental load of a process when several products or functions share the same process. And, the impact categories chosen. Life cycle inventory. Life cycle inventory analysis involves creating an inventory of flows from and to nature for a product system. Inventory flows include inputs of water, energy, and raw materials, and releases to air, land, and water. To develop the inventory, a flow model of the technical system is constructed using data on inputs and outputs. The flow model is typically illustrated with a flow chart that includes the activities that are going to be assessed in the relevant supply chain and gives a clear picture of the technical system boundaries. The input and output data needed for the construction of the model are collected for all activities within the system boundary, including from the supply chain. The data must be related to the functional unit defined in the goal and scope definition. Data can be presented in tables and some interpretations can be made already at this stage. The results of the inventory is an LCI which provides information about all inputs and outputs in the form of elementary flow to and from the environment from all the unit processes involved in the study. Inventory flows can number in the hundreds depending on the system boundary. For product LCAs at either the generic or brand-specific level, that data is typically collected through survey questionnaires. At an industry level, care has to be taken to ensure that questionnaires are completed by a representative sample of producers, leaning toward neither the best nor the worst, and fully representing any regional differences due to energy use, material sourcing or other factors. The questionnaires cover the full range of inputs and outputs, typically aiming to account for 99% of the mass of a product, 99% of the energy used in its production and any environmentally sensitive flows, even if they fall within the 1% level of inputs. One area where data access is likely to be difficult is flows from the technosphere. The technosphere is more simply defined as the man-made world. Considered by geologists as secondary resources, these resources are in theory 100% recyclable. However, in a practical sense the primary goal is salvage. For an LCI, these technosphere products are those that have been produced by man and unfortunately those completing a questionnaire about a process which uses man-made product as a means to an end will be unable to specify how much of a given input they use. Typically, they will not have access to data concerning inputs and outputs for previous production processes of the product. The entity undertaking the LCA must then turn to secondary sources if it does not already have that data from its own previous studies. National databases or datasets that come with LCA practitioner tools, or that can be readily accessed, are the usual sources for that information. Care must then be taken to ensure that the secondary data source properly reflects regional or national conditions. Life cycle impact assessment. Inventory analysis is followed by impact assessment. This phase of LCA is aimed at evaluating the significance of potential environmental impacts based on the LCI flow results. Classical life cycle impact assessment consists of the following mandatory elements: selection of impact categories, category indicators, and characterization models. The classification stage, where the inventory parameters are sorted and assigned to specific impact categories. And impact measurement, where the categorized LCI flows are characterized, using one of many possible LCIA methodologies, into common equivalence units that are then summed to provide an overall impact category total. In many LCAs, characterization concludes the LCIA analysis. This is also the last compulsory stage according to ISO 14044-2006. However, in addition to the above mandatory LCIA steps, other optional LCIA elements normalization, grouping, and weighting may be conducted depending on the goal and scope of the LCA study. In normalization, the results of the impact categories from the study are usually compared with the total impacts in the region of interest, the US for example. Grouping consists of sorting and possibly ranking the impact categories. During weighting, the different environmental impacts are weighted relative to each other so that they can then be summed to get a single number for the total environmental impact. ISO 14044-2006 generally advises against weighting, stating that a weighting shall not be used in LCA studies intended to be used in comparative assertions intended to be disclosed to the public. This advice is often ignored, resulting in comparisons that can reflect a high degree of subjectivity as a result of weighting. Interpretation. Life cycle interpretation is a systematic technique to identify, quantify, check, and evaluate information from the results of the life cycle inventory and/or the life cycle impact assessment. The results from the inventory analysis and impact assessment are summarized during the interpretation phase. The outcome of the interpretation phase is a set of conclusions and recommendations for the study. According to ISO 14040-2006, the interpretation should include identification of significant issues based on the results of the LCI and LCIA phases of an LCA, evaluation of the study considering completeness, sensitivity and consistency checks, and conclusions, limitations and recommendations. A key purpose of performing life cycle interpretation is to determine the level of confidence in the final results and communicate them in a fair, complete, and accurate manner. Interpreting the results of an LCA is not as simple as 3 is better than 2, therefore alternative A is the best choice. Interpreting the results of an LCA starts with understanding the accuracy of the results, and ensuring they meet the goal of the study. This is accomplished by identifying the data elements that contribute significantly to each impact category, evaluating the sensitivity of these significant data elements, assessing the completeness and consistency of the study, and drawing conclusions and recommendations based on a clear understanding of how the LCA was conducted and the results were developed. Reference test, more specifically, the best alternative is the one that the LCA shows to have the least cradle-to-grave environmental negative impact on land, sea, and air resources. LCA uses, based on a survey of LCA practitioners carried out in 2006. LCA is mostly used to support business strategy and R&D, as input to product or process design, in education and for labeling or product declarations. LCA will be continuously integrated into the built environment as tools such as the European Inchlik Building Project Guidelines for Buildings or developed and implemented, which provide practitioners guidance on methods to implement LCA data into the planning and design process. Major corporations all over the world are either undertaking LCA in-house or commissioning studies, while governments support the development of national databases to support LCA. Of particular note is the growing use of LCA for ISO Type 3 labels called Environmental Product Declarations, defined as quantified environmental data for a product with preset categories of parameters based on the ISO 14040 series of standards, but not excluding additional environmental information. These third-party certified LCA-based labels provide an increasingly important basis for assessing the relative environmental merits of competing products. Third-party certification plays a major role in today's industry. Independent certification can show a company's dedication to safer and environmental-friendlier products to customers and NGOs. LCA also has major roles in environmental impact assessment, integrated waste management and pollution studies. Data analysis. A life cycle analysis is only as valid as its data. Therefore, it is crucial that data used for the completion of a life cycle analysis are accurate and current. When comparing different life cycle analyses with one another, it is crucial that equivalent data are available for both products or processes in question. If one product has a much higher availability of data, it cannot be justly compared to another product which has less detailed data. There are two basic types of LCA data: unit process data and environmental input-output data, where the latter is based on national economic input-output data. Unit process data are derived from direct surveys of companies or plants producing the product of interest, carried out at a unit process level defined by the system boundaries for the study. Data validity is an ongoing concern for life cycle analyses. Due to globalization and the rapid pace of research and development, new materials and manufacturing methods are continually being introduced to the market. This makes it both very important and very difficult to use up-to-date information when performing an LCA. If an LCA unregistered trademark's conclusions are to be valid, the data must be recent. However, the data gathering process takes time. If a product and its related processes have not undergone significant revisions since the last LCA data was collected, data validity is not a problem. However, consumer electronics such as cell phones can be redesigned as often as every 9 to 12 months, creating a need for ongoing data collection. The life cycle considered usually consists of a number of stages including materials extraction, processing and manufacturing, product use, and product disposal. If the most environmentally harmful of these stages can be determined, then impact on the environment can be efficiently reduced by focusing on making changes for that particular phase. For example, the most energy-intensive life phase of an airplane or car is during use due to fuel consumption. One of the most effective ways to increase fuel efficiency is to decrease vehicle weight, and thus, car and airplane manufacturers can decrease environmental impact in a significant way by replacing aluminum with lighter materials such as carbon fiber reinforced fibers. the reduction during the use phase should be more than enough to balance additional raw material or manufacturing cost. Variants, cradle-to-grave. Cradle-to-grave is the full life cycle assessment from resource extraction to use phase and disposal phase. For example, trees produce paper, which can be recycled into low-energy production cellulose insulation, then used as an energy-saving device in the ceiling of a home for 40 years, saving 2,000 times the fossil fuel energy used in its production. After 40 years the cellulose fibers are replaced and the old fibers are disposed of, possibly incinerated. All inputs and outputs are considered for all the phases of the life cycle. Cradle-to-gate. Cradle-to-gate is an assessment of a partial product life cycle from resource extraction to the factory gate. The use phase and disposal phase of the product are omitted in this case. Cradle-to-gate assessments are sometimes the basis for environmental product declarations termed business-to-business EDPs. One of the significant uses of the cradle-to-gate approach compiles the life cycle inventory using cradle-to-gate. This allows the LCA to collect all of the impacts leading up to resources being purchased by the facility. They can then add the steps involved in their transport to plant and manufacture process to more easily produce their own cradle-to-gate values for their products. Cradle-to-cradle or closed-loop production. Cradle-to-cradle is a specific kind of cradle-to-grave assessment, where the end-of-life disposal step for the product is a recycling process. It is a method used to minimize the environmental impact of products by employing sustainable production, operation, and disposal practices and aims to incorporate social responsibility into product development. From the recycling process originate new, identical products, or different products. Allocation of burden for products in open-loop production systems presents considerable challenges for LCA. Various methods, such as the avoided burden approach, have been proposed to deal with the issues involved. Gate-to-gate. Gate-to-gate is a partial LCA looking at only one value-added process in the entire production chain. Gate-to-gate modules may also later be linked in their appropriate production chain to form a complete cradle-to-gate evaluation. Well-to-wheel. Well-to-wheel is the specific LCA used for transport fuels and vehicles. The analysis is often broken down into stages entitled well-to-station, or well-to-tank, and station-to-wheel, or tank-to-wheel, or plug-to-wheel. The first stage, which incorporates the feedstock or fuel production and processing and fuel delivery or energy transmission, and is called the upstream stage, while the stage that deals with vehicle operation itself is sometimes called the downstream stage. The well-to-wheel analysis is commonly used to assess total energy consumption, or the energy conversion efficiency and emissions impact of marine vessels, aircraft and motor vehicles, including their carbon footprint, and the fuels used in each of these transport modes. The well-to-wheel variant has a significant input on a model developed by the Argonne National Laboratory. The greenhouse gases, regulated emissions, and energy use in transportation model was developed to evaluate the impacts of new fuels and vehicle technologies. The model evaluates the impacts of fuel use using a well-to-wheel evaluation, while a traditional cradle-to-grave approach is used to determine the impacts from the vehicle itself. The model reports energy use, greenhouse gas emissions, and 6 additional pollutants, volatile organic compounds, carbon monoxide, nitrogen oxide, particulate matter with size smaller than 10 micrometer, particulate matter with size smaller than 2.5 micrometer, and sulfur oxides. Economic input-output life cycle assessment. Economic input-output LCA involves use of aggregate sector-level data on how much environmental impact can be attributed to each sector of the economy and how much each sector purchases from other sectors. Such analysis can account for long chains, which somewhat alleviates the scoping problem of process LCA. However, any LCA relies on sector-level averages that may or may not be representative of the specific subset of the sector relevant to a particular product and therefore is not suitable for evaluating the environmental impacts of products. Additionally, the translation of economic quantities into environmental impacts is not validated. Ecologically based LCA. While a conventional LCA uses many of the same approaches and strategies as an eco-LCA, The latter considers a much broader range of ecological impacts. It was designed to provide a guide to wise management of human activities by understanding the direct and indirect impacts on ecological resources and surrounding ecosystems. Developed by Ohio State University Center for Resilience, ECO-LCA is a methodology that quantitatively takes into account regulating and supporting services during the life cycle of economic goods and products. In this approach, services are categorized in four main groups: supporting, regulating, provisioning and cultural services. Life cycle energy analysis. Life cycle energy analysis is an approach in which all energy inputs to a product are accounted for, not only direct energy inputs during manufacture, but also all energy inputs needed to produce components, materials and services needed for the manufacturing process. An earlier term for the approach was energy analysis. With LCEA, the total life cycle energy inputs is established. Energy production. It is recognized that much energy is lost in the production of energy commodities themselves, such as nuclear energy, photovoltaic electricity or high-quality petroleum products. Net energy content is the energy content of the product minus energy input used during extraction and conversion, directly or indirectly. A controversial early result of LCEA claimed that manufacturing solar cells requires more energy than can be recovered in using the solar cell. The result was refuted. Another new concept that flows from life cycle assessments is energy cannibalism. Energy cannibalism refers to an effect where rapid growth of an entire energy-intensive industry creates a need for energy that uses the energy of existing power plants. Thus, during rapid growth, the industry as a whole produces no energy because new energy is used to fuel the embodied energy of future power plants. Work has been undertaken in the UK to determine the life cycle energy impacts of a number of renewable technologies. Energy recovery. If materials are incinerated during the disposal process, the energy released during burning can be harnessed and used for electricity production. This provides a low-impact energy source, especially when compared with coal and natural gas. While incineration produces more greenhouse gas emissions than landfilling, the waste plants are well fitted with filters to minimize this negative impact. A recent study comparing energy consumption and greenhouse gas emissions from landfilling against incineration found incineration to be superior in all cases except for when landfill gas is recovered for electricity production. Criticism. A criticism of LCEA is that it attempts to eliminate monetary cost analysis, that is, replace the currency by which economic decisions are made with an energy currency. It has also been argued that energy efficiency is only one consideration in deciding which alternative process to employ, and that it should not be elevated to the only criterion for determining environmental acceptability. For example, simple energy analysis does not take into account the renewability of energy flows or the toxicity of waste products. However, the life cycle assessment does help companies become more familiar with environmental properties and improve their environmental system. Incorporating dynamic LCAs of renewable energy technologies may help mitigate this criticism. In recent years, the literature on life cycle assessment of energy technology has begun to reflect the interactions between the current electrical grid and future energy technology. Some papers have focused on energy life cycle, while others have focused on carbon dioxide and other greenhouse gases. The essential critique given by these sources is that when considering energy technology, the growing nature of the power grid must be taken into consideration. If this is not done, a given class of energy technology may emit more carbon dioxide over its lifetime than it mitigates. A problem the energy analysis method cannot resolve is that different energy forms have different quality and value even in natural sciences, as a consequence of the two main laws of thermodynamics. A thermodynamic measure of the quality of energy is exergy. According to the first law of thermodynamics, all energy inputs should be accounted with equal weight, whereas by the second law diverse energy forms should be accounted by different values. The conflict is resolved in one of these ways: value difference between energy inputs is ignored, a value ratio is arbitrarily assigned, the analysis is supplemented by economic cost analysis, exergy instead of energy can be the metric used for the life cycle analysis. Critiques. Life cycle assessment is a powerful tool for analyzing commensurable aspects of quantifiable systems. Not every factor, however, can be reduced to a number and inserted into a model. Rigid system boundaries make accounting for changes in the system difficult. This is sometimes referred to as the boundary critique to systems thinking. The accuracy and availability of data can also contribute to inaccuracy. For instance, data from generic processes may be based on averages, unrepresentative sampling, or outdated results. Additionally, social implications of products are generally lacking in LCAs. Comparative life cycle analysis is often used to determine a better process or product to use. However, because of aspects like differing system boundaries, different statistical information, different product uses, etc., these studies can easily be swayed in favor of one product or process over another in one study and the opposite in another study based on varying parameters and different available data. There are guidelines to help reduce such conflicts in results, but the method still provides a lot of room for the researcher to decide what is important, how the product is typically manufactured, and how it is typically used. An in-depth review of 13 LCA studies of wood and paper products found a lack of consistency in the methods and assumptions used to track carbon during the product lifecycle. A wide variety of methods and assumptions were used, leading to different and potentially contrary conclusions, particularly with regard to carbon sequestration and methane generation in landfills and with carbon accounting during forest growth and product use. Streamline LCA. This process includes 3 steps. First, a proper method should be selected to combine adequate accuracy with acceptable cost burden in order to guide decision-making. Actually, in LCA process, besides streamline LCA, eco-screening and complete LCA are usually considered as well. However, the former one only could provide limited details and the latter one with more detailed information is more expensive. Second, single measure of stress should be selected. Typical LCA outputs includes resource consumption, energy consumption, water consumption, emission of CO2, toxic residues and so on. One of these outputs is used as the main factor to measure and streamline LCA. Energy consumption and CO2 emission are often regarded as a practical indicators. Last, stress selected in Step 2 is used as standard to assess phase of life separately and identify the most damaging phase. For instance, for a family car, energy consumption could be used as the single stress factor to assess each phase of life. The result shows that the most energy-intensive phase for a family car is usage stage. See also. References. Further reading: Van Veeden, G. Horschild, M. Ekval, T. Gurney, J. Hujungs, R. Helweg, S. Kaya, A. Pennington, D. Su, S. Recent Developments in Life Cycle Assessment. Journal of Environmental Management 91, 1 21 doi, 10.1016/J. Gendman. 2009.06.018. Retrieved October 31, 2012. Bowe, Scott. A Gate-to-Gate Lifecycle Inventory of Solid Hardwood Flooring in the Eastern US. Wood and Fiber Science, March 2010. Society of Wood Science and Technologue. Retrieved October 25, 2011. Thomas, J. A. G., ed., Energy Analysis, IPC Science and Technology Press and Westview Press, 1977, ISBN 0-902-2852-60-4 or ISBN 0-89158-813-2, Carnegie Mellon. EIOLCA, Free, Fast, Easy Life Cycle Assessment. Retrieved October 31, 2012. Crawford, R. H. Life Cycle Assessment in the Built Environment, London, Taylor and Francis. M. W. Gilliland ed., Energy Analysis, A New Public Policy Tool, AAA Selected Symposia Series, Westview Press, Boulder, Colorado, 1978, ISBN 0-89158-437-4 Center for Life Cycle Analysis, Columbia University, New York, Jachner Copyright E. ed., Handbook on Life Cycle Assessment, Operational Guide to the ISO Standards, Kluwer Academic Publishers, 2002. Hendrickson, C.T., Lave, L.B., and Matthews, H.S. Environmental Life Cycle Assessment of Goods and Services, an Input-Output Approach, Resources for the Future Press. Bowman, H. Hodge Tilghman, A.M. The Hitchhiker's Guide to LCAA and Orientation in Life Cycle Assessment Methodology and Application. 2004. ISBN 91-44-02364-2, Crawford, R.H. Validation of a Hybrid Lifecycle Inventory Analysis Method, Journal of Environmental Management, 88, 3, 496 Euro 506. Jimenez Gonzalez, C. A. al. 2004. Cradle-to-Gate Life Cycle Inventory and Assessment of Pharmaceutical Compounds. INTRJ LCA. 9, 2, 114 Euro 121. Curran, Mary A. Environmental Life Cycle Assessment, McGraw-Hill Professional Publishing, 1996, ISBN 978-0-07-0150638, Kim, S. and Dale, B. Life Cycle Assessment of Various Cropping Systems Utilized for Producing Biofuels, Bioethanol and Biodiesel. Biomass and Bioenergy 2005, 29, 426 Euro 439. Sion-Brown, D.F. Environmental Life Cycle Analysis. Boca Raton, Florida, CRC Press. ISBN 1-56670-214-3. Horn, Ralph, A. al. LCA, Principles, Practice and Prospects. CSIRO Publishing, Victoria, Australia, 2009, ISBN 0-643-09452-0. Trusty, Wayne, A Euro-OE An Overview of Life Cycle Assessments, Part O Neo Euro, International Code Council Building Safety Journal Online, October 2010, http, BSJXA-Fork Features LCA HTML. Valero, Daniel A. and Brazier, Chris, Sustainable Design, The Science of Sustainability and Green Engineering, John Wiley & Sons, Incorporated, Hoboken, New Jersey, ISBN 0470130628. 350 pages. Vigon, B.W. Life Cycle Assessment, Inventory Guidelines and Principles. Boca Raton, Florida, CRC Press. ISBN 1-56670-015-9. Vogtler Currency J.G., A Euro-OEA Practical Guide to LCA for Students, Designers, and Business Managers. A Euro, VSSD, 2010, ISBN 978-90-6562-253-2. Zamagnai, Alessandra. Life Cycle Sustainability Assessment, The International Journal of Life Cycle Assessment, 17, 4, 373-376. External links: the European Commission's Directory of LCA Services, Tools, Databases, and Provider, the European Commission's LCA Database ELCD, UNEPS-ETAC Life Cycle Initiative. A stakeholder-financed project, Department Life Cycle Engineering. A Euro LBP. A Euro University of Stuttgart. Embodied Energy, Life Cycle Assessment. Your Home Technical Manual. A joint initiative of the Australian Government and the design and construction industries. At the Wayback Machine, LCA Research at the Centre for Environmental Sciences, Leiden University. Explanation of LCA from the American Chemistry Council, the National Risk Management Research Laboratory's LCA website. What is Life Cycle Assessment? White Paper, LCA Example, Light Emitting Diode from GSA Sustainable Facilities Tool.